We're now going to take a look at finding the derivative of inverse trigonometric functions. And this is a big moment for us because once we've completed this task of differentiating inverse trig functions, we would have now been able to compute the derivative for all the standard functions studied in algebra and trig. So we should be proud of ourselves, right? So just as how there are six trigonometric functions and we can now differentiate all six, there are six inverse trigonometric functions. And what I'm going to do is derive two of the derivatives, and then I'll state the remaining four. The remaining four are very similar in process, but I'm just going to focus on finding the derivative of arcsine or inverse sine, and then also arctangent or inverse tangent, because arguably those are the two most important ones that show up not just in say the differential calculus but also integral calculus. That will be your second semester of calculus. Okay, so let's get started. So this is our first goal. We want to be able to find the derivative of arcsine, right? Well, what do we know about arcsine? Let me just remind you of a couple basic properties. We know, for one, that its domain consists of all real numbers between and including plus or minus 1, right? So the domain of arcsine, all values of x between and including plus or minus 1, and the range, right? So the range, so like what values of y can be obtained by evaluating this function at these values of x? Well, you end up getting values between negative pi over 2 and positive pi over 2, right? What else? Well, what about the graph? The graph of this function, pretty interesting. And if we now, when we plot it, we're only going to see this function defined for values of x between plus or minus 1. So that's where the domain would be, and then the range, basically it ranges from negative pi over 2 up to pi over 2, right? And the shape is kind of interesting. It starts out down here, kind of curves up like this, and then curves up like that. And that's it. So that's the graph of arcsine, right? I mean, nothing super fancy, but this is the function whose derivative we're now going to try to find. Now, before we get to the calculus, I just want to say a couple more things about the trig. Now, there are some important identities, so for instance, we know that the sine squared of y plus cosine squared of y, that's equal to 1, right? So that's an important identity. And we're actually going to make use of this, right? So on the right here, what I have are just some useful facts about this arcsine function, and then we have our Pythagorean identity right here. Now, we don't know how to differentiate arcsine. That's what we're trying to accomplish in this video. But we do know how to differentiate sine, and we do know how to differentiate implicitly. So what we do is take the sine of both sides of this equation, right? So if we do that, well, by definition, for all values of x between plus or minus 1 and including plus or minus 1, sine and arcsine are inverse functions, so they cancel each other out, right? So they cancel each other out. So what I have on the right-hand side is this, right? So it's now an implicit curve because I don't have my dependent variable isolated. But remember, we still assume that y is a function of x. So then if I differentiate both sides with respect to x, so if I differentiate, again, with respect to, so WRT is a common abbreviation for with respect to x. Well, on this side, I'll have to use my chain rule because of the composite, because I have sine of y of x. So I need my chain rule on this side. Well, this derivative on this side is relatively easy. It's just going to be equal to 1. So let's write that down. Right, so apply my chain rule here. I know that the derivative of sine is cosine. The chain rule says keep my inner function and then multiply by the derivative of my inner function. And then when I differentiate my x, I'll get 1. Right? So now if I go back and write it in the form where I just have my dependent variable, instead of explicitly saying y of x, if I just switch back to my basic y equation, this is what this equation looks like. Right? So I have the cosine of y times dy dx, that's equal to 1. So again, not a terribly complicated equation. Next up, what I can do is differentiate, not differentiate, but divide both sides by the cosine of y. That way I can isolate dy dx. So I'll get that dy dx is 1 over the cosine of y, right? Well, I mean, as far as derivatives go, that's not terribly complicated, but since our original function was in terms of x, it would be nice to get this in terms of x as well, right? Well, here we have the cosine of y, right? So we have the cosine of y. Over here, we have an equation that has the cosine of y squared. So maybe what I can do is take my Pythagorean identity, isolate cosine of y, and see if I can get that in terms of x. All right, so let's walk through those steps. So I can subtract the sine of y squared from both sides. Right, so this tells me that cosine of y squared is equal to 1 minus the sine of y squared. And then if I'm going to take the derivative, I'm sorry, not the derivative, if I'm trying to isolate cosine of y, I would have to take my square root, right? So I'd have to do that the cosine of y is plus or minus the square root of 1 minus sine squared of y. Now, let's think about this for a second. Here's the range of y. So right here are the possible values of y. This tells me that y is in the, so if I put this in my, let's say my quadrants, negative pi over 2 is down here, and positive pi over 2 is up here, and we're looking at all the values in this range. So this range of values for y tells me that y is in the first and fourth quadrants, right? But in the first and fourth quadrants, cosine is always positive, right? So in these quadrants, right, cosine is always positive. Well, what does that mean? Well, it means I have to get rid of the negative in front of my square root, right? Because this side is always positive, so I certainly can't have anything negative on this side. So since the cosine of y is greater than or equal to 0 in quadrants 1 and 4, then what I have here is an expression that says the cosine of y is the square root of 1 minus sine squared of y. All right? So we're able to get rid of that negative sign, again, because of this range. And that's why it's so important to have these fundamental properties in mind, because they tend to come up as you work through other problems. Okay. Okay, so well, how does this help? Well, look, we know that the sine of y is equal to x. So wherever I have the sine of y, so let me write this a little bit more clearly. Under the square root, we have 1 minus the sine of y, and then it's all squared. That's what this notation is telling me. So if I take the sine of y and replace it with x, right, I can put an x right here, right? And then I have this nice expression for the cosine of y. It will be the square root of 1 minus x squared. So then I can put this root in the denominator and get my derivative in terms of x, right? So we're kind of bouncing back and forth using identities, using all these properties, but in the end, this is what we've come up with. All right, so let's write it down. As always, let's do our little summary. So if y is arc sine of x, then its derivative, dy dx, is 1 over the square root of 1 minus x squared, right? Now, again, I stated the domain earlier. Let me state it again. Over here, for the function, its domain, all real numbers between and including plus or minus 1. However, I can't evaluate this derivative at these endpoints, because at the endpoints the denominator is 0. So in fact, even though the function is defined on the closed interval, it's only differentiable on the open interval, right? So this is valid for all values of x, oh, no equal sign, so all values of x that are strictly between plus or minus 1, right? So again, this is a nice little illustration that even though the function might be defined on a certain interval, it might not be differentiable on that same interval, all right? Okay, good, so we have our derivative. Derivative of arcsine is 1 over the square root of 1 minus x squared. Right? As promised, I want to show you how we get to the derivative of arctangent. Again, arguably, those are the two most important inverse trig derivatives that you'll utilize in your study of calculus. Not that the other ones aren't important, but again, these are the ones you'll see the most, right? So next up, let's look at arctangent. And let's pretty much do the same thing. Let's talk about its domain, let's talk about its range. Let's see what's going on. Well, earlier when we were talking about continuity and so forth, we discussed arctangent and the fact that its domain is all real values of x. So unlike arcsine and also arccosine, arctangent is defined for all values of x. And its range, however, interestingly, is exactly the same range as arcsine. It ranges from negative pi over 2, but the thing though is, it can't be equal, so it's strictly between negative pi over 2 and pi over 2. And you might remember that arctangent has a pair of horizontal asymptotes. Here's the graph of the arctangent function, just the basic one. it has those horizontal asymptotes at positive pi over 2 and negative pi over 2, right? That's a negative sign. And then the graph, it starts out down here, goes up, passes through the origin, and then goes up here and just kind of flattens out, right? So it starts out pretty flat, steepens up a little bit, passes through the origin, flattens out after. Right? All right, so again, standard facts about the arctangent function, its basic graph. So what identities do we know that involve tangent? Well, there's another version of the Pythagorean identity that is in terms of tangent and secant. And the basic one is that 1 plus tangent squared of y is equal to secant squared of y, right? And we are going to make use of this one as well, right? All right, so let's see. So let's follow the same trick. And the reason we use this trick is because we know how to differentiate the trig functions and we know how to differentiate implicitly. Use those two techniques. So essentially what we want to do is convert this equation into an implicit equation that's in terms of tangent as opposed to arctangent, right? So take the tangent of both sides. So the tangent of y is equal to the tangent of the arctangent of x. But again, these are inverse functions. So we're left with x on the right-hand side, and then we have the tangent of y on the left. So it looks very, very similar to what we did previously. And then, again, just as a reminder, let's write this, as a reminder that yes, y is dependent on x. I mean, we can see it up here, right? We can see the dependency. The only reason why we switch it into the implicit form is because we know how to differentiate tangent, right? Okay, so now that we have this particular form, let's differentiate again with respect to x, WRT x. Now let's think about it. What's the derivative of tangent? That's secant squared. So we'll have secant squared, and by the chain rule, again we keep the inner function, and then we multiply by the derivative of the inner function. So that's the derivative on the left, and then the derivative on the right is 1. Notice how with a lot of these, when we switch from the inverse function back to the original function, we end up having a 1 on this side, right? And you'll see that pattern with all our inverse functions, right? In fact, we saw it with the logarithmic function, which is an inverse of our exponential function. So it seems like all these inverse functions, they end up having 1 over something. Pretty interesting. All right, so let's see if we can continue and simplify this. So if let's divide both sides by secant squared, right? And then I'll switch back to the y, just the y equation form or notation. So secant squared of y. But if we look at this, we don't even need a square root now, right? So we have the secant squared that is equal to 1 plus tangent squared, but tangent is equal, or the tangent of y is equal to x. So what I can do here is just write this. So 1 plus x squared is equal to secant squared of y. So then, yeah, I can replace this secant squared of y with 1 plus x squared, and that's the famous derivative of arctangent. All right. Now, let me write it down, and we also, let's think about the domain here, right? So if y is equal to arctangent of x, and we just proved that its derivative is 1 over 1 plus x squared. Right? I remember what we had said, that this function has a domain of all real values of x. Well, taking the derivative, it's still all real values of x. Because even though we now have this expression in the denominator, this denominator can never be 0. In fact, the smallest this denominator can be is a positive 1, because we're squaring a real number and then we're adding 1, right? So this derivative is valid also for all values of x, right? So it's not every inverse trig function somehow the domain is different, or the domain of the function is different from the domain of its inverse. This result is showing that the arctangent function is also differentiable at all values of x. All right? Okay, so let me just kind of state the remaining 4. Right, so I'll just go ahead and write these down. So we did arcsine. In fact, let me state all 6 together. And what I'll do is, so this is basically our summary of all of these. And I'll go ahead and just state it like this. So the derivative of arcsine, that is 1 over the square root of 1 minus x squared. The derivative of arctangent, that's the second one that we derived. That is 1 over 1 plus x squared. Now, the derivative of arcsecant, again, not necessarily a function that you use a lot, but it is a derivative that we have to know. And I mean, when you look at it, it seems to be the most complicated of the 3. In the denominator, you have an absolute value of x, and then you have the square root of x squared minus 1. Right? Now, see, for what values of x are these functions well defined, meaning the derivatives? Well, this one, as we said earlier, is valid for all values of x strictly between plus or minus 1. This one we stated earlier that it's valid for all real numbers. This one, because if you notice the expression under the radical is switched. Oh, for arcsine it's 1 minus x squared under the square root, whereas for arcsecant it's x squared minus 1. What that means is your x would have to be outside of this interval. So your x would either have to be bigger than 1 or less than -1 for this function to be well defined. If x doesn't satisfy either of these inequalities, you're going to end up with a negative under the square root. And since we're only using real numbers, then we can't allow that to happen, right? So those are the 3. Now again, if you remember when I did the trig functions, we pretty much did all the trig functions that don't start with the letter C. So we didn't do the co ones. I wrote down essentially these first, the sine, the tangent, and secant, and then we did, okay, cosine, cotangent, cosecant. And I'll do exactly the same thing here. And what is pretty remarkable, if you remember the pattern from derivatives of the trig functions, the co-ratios just had a negative sign. Well, not just, but they all had a negative sign in front. And that's exactly what happens with the remaining 3 inverse trig functions. So, and they're also valid on the same domain. So I'm not going to state the domains again, but the derivative of arc cosine ends up being -1 over the square root of 1 minus x squared. The derivative of arc cotangent, that ends up being negative 1 over 1 plus x squared. And then finally, the derivative of arc cosecant is negative 1 over, again, absolute value of x times the square root of x squared minus 1, right? And again, if you're wondering why do the negatives come up, well, the trick for these would be very similar. We would work with the, for instance, here we would work with the cosine of y, and that would be equal to x. But I know that when I differentiate the co-ratios, I always get a negative in front of my expression, and that's why these negatives end up being a part of the answer, right? So it's not sort of magical, where do these negatives come from? They come from the fact that when you differentiate the co-trigonometric ratios, they have negative signs in them. All right? Okay, so I think probably a good thing to do is let's do a few examples of this. Let's see how it works. Right? And let's scroll down a little bit here. And let's do some examples of this. All right, so let's say our first function, as usual, arc sine of something that's more complicated than x, right? So let's start out with the x squared minus 3x plus 1, right? So there's a composite. And again, it's usually helpful, like when you learn a new set of derivative rules, and let's say you realize, oh, I have a composite now, I have to do my chain rule. Maybe the first one or two, use the first version of the chain rule just to get a sense of how everything comes together. And then again, as you get more comfortable and more experience, you can switch to the second version of the chain rule. So here what I'll say is let u be equal to x squared minus 3x plus 1. And then that means my y equation is the arc sine of u. And again, we now have rules to differentiate both these types of functions, right? So du dx is 2x minus 3. dy du is now our 1 over the square root of 1 minus u squared. So then if I want to find the derivative of y with respect to x, the first version of the chain rule says I multiply these two derivatives. So dy dx is equal to dy du times du dx. So dy du is the reciprocal of the square root of 1 minus u squared, and then I have to multiply by the quantity 2x minus 3. So two things I'll do. First is I'll put the 2x minus 3 over 1, and then second, as always, since we want our final answer to be in terms of x, wherever there's a u in my derivative, I'm going to replace it with the quantity x squared minus 3x plus 1. And again, this is us forming another composite. So we're going to replace the variable in this function with another function, right? So here's our final answer, and I'll write it, we'll just write it in the line below. So dy dx is 1 over the square root of 1 minus, and now I'll write the quantity x squared minus 3x plus 1 squared, again times the quantity 2x minus 3 over 1. So then I can write this as a single fraction with a numerator of 2x minus 3 and a denominator of the square root of 1 minus the quantity x squared. minus 3x plus 1 squared. So x squared minus 3x plus 1 squared, right? And there's really no need, I mean, you can, if you just like to FOIL things out, you can go ahead and expand this trinomial, but again, it's not going to take you much further to anything that's simplified or more simplified than this. Having that square root there makes it harder to simplify. So we're going to leave our answer in this particular form. All right. Let's try this, or second example. Let's say that y is equal to e to the z times the arctangent of 2z. All right. I'm just, again, wanting to use a slightly different letter, right? That way we don't get fixated on x, but we pay more attention to the functions and the operations, and then what rules are needed to find the derivative. So we need a product rule for sure, and we're also going to need the chain rule, because again, there's another composite, because it's arctangent of 2z. So let's start by writing down what the product rule says. So dy dz, the derivative of the first, well, that's e to the z, times the second, and then plus the first, which again is e to the z, and now one of our newest derivatives. So let's see if we can use the second version of our chain rule. So when you differentiate arctangent, you get 1 over 1 plus something squared. But now it's not just an x, there's a 2z inside the arctangent function. So it's 1 over 1 plus the quantity 2z squared. And then the chain rule says, I have to multiply by the derivative of what's inside. So I have to take the derivative of 2z with respect to z. Well, that's going to be 2. Right? So let's see how this simplifies. We have e to the z times the arctangent of 2z plus, now as far as the fraction here, we have an e to the z and we have a 2, and all these numerators are being multiplied, so that's 2e to the z, and then it's over 1 plus. Now this is a lot easier to simplify than this quadratic squared that we had earlier. Well, the quantity 2z squared is 4z squared, right? And that's our derivative. Now, if you wanted to write this as a single fraction, well, you're going to have to get a common denominator, and that actually makes the expression even look a little bit more complicated, because I would have to multiply the bottom and the top of this fraction by the entire quantity 1 plus 4z squared. But this is what it looks like written as a single fraction. So we have the e to the z times the arctangent of 2z, and then times the quantity 1 plus 4z squared, and then plus, and there's no change to this numerator, so 2 e to the z. Alright, so here's our third and final one. So let's say we have y be equal to arcsecant of e to the 3x, right? So this is a function where we're actually going to have to apply the chain rule twice, because, I mean, listen to how I say it. It's arcsecant of e to the 3x. So again, we have e raised to this power, which is another function, and then we have that entire exponential function inside the arcsecant, right? So let's see if we can write down what this derivative is using our chain rule twice. So dy dx is, so now we have to remember our special rule for differentiating arc secant? Well, it's 1 over the absolute value of something times the square root of something squared minus 1. So these are just like placeholders. These are placeholders. Well, what goes in these places? It's whatever the inner function is. So it will be the absolute value of e to the 3x times the square root of e to the 3x squared minus 1. And then I have to multiply by the derivative of e to the 3x. Differentiating e to the 3x gives us back e to the 3x, and then I have to multiply by 3 again because of the chain rule, right? So multiple applications of the chain rule, and with the inverse trig functions, you have to be really careful, particularly with the arcsecant, of where you plug the inner function back in, right? So let's see if we can write this in any kind of simpler form, right? Well, the numerator isn't too bad. It's 3e to the 3x. In the denominator, now e to the 3x, this is a property of exponential functions, e to the 3x is always positive. So the absolute value of something positive just returns that same thing. So what this means is that the absolute value of e to the 3x is still e to the 3x, right? In fact, there are some times when if you're assuming that your variable is always positive, many times the derivative of arcsecant, the absolute value is actually left out, right? But in this case, we have another reason why it's left out, and that's because the e to the 3x is always positive, right? And now under the square root, what do we have? Well, to simplify e to the 3x that squared, we multiply those exponents and we get e to the 6x. So when we put it all together, here is our simplified derivative of this function, right? So lots of exponential functions, but in the grand scheme of things, this is certainly not the most complicated derivative we've seen. In fact, I would say just look at the previous derivative. This one looks messier, right? But anyway, that's our derivative of arcsecant of e to the 3x. So hopefully those 3 examples kind of gives you a sense of what's involved when differentiating these inverse trigonometric functions. And now we should be really proud, right? We can differentiate, in theory, any function that's put in front of us, right? See you in the next video.